Hello everyone. So my name is Pawan. I am from the Indian Institute of Science, Center for Nano. I am a faculty at the Center for Nanoscience and Engineering. So welcome to this NPTEL course, and the name of the course is Design Principles for Electronic, Electromechanical and Optical Devices. So before delving into what this course is all about, so let me just first give you a brief overview of what sort of audience does this course cater to. So the department I come from in IISc is actually an interdisciplinary department. It has people from mechanical engineering, electronics engineering, physicists, materials engineering, biologists and so on and so forth. So it's quite a broad interdisciplinary platform, and this is a materials course designed for such an interdisciplinary audience. So you'll find aspects of fundamental physics, you'll find aspects of material science, you'll find aspects of bit of electronics engineering and so on and so forth, mechanical engineering and so on and so forth in this course. So it actually does cater to a wide variety of interdisciplinary audience, but the motto of the course is to introduce to you how materials properties come about, and by the end of the course the expectation, or so the way I want to leave you is, if there is a new problem in mind, so I want a material that should be piezoelectric, that should have so and so's piezoelectric coefficient and so on and so forth. So I should be able to engineer a material of choice in using conventional techniques of what are called of materials engineering, to be able to design these properties, right. So that will be the eventual motto of this course. So I will go into details in this lecture about what this course is going to be all about. But before that, let me start by so what are the references that I will follow in this course. So as always in all my courses, so I make the course, so this course is designed by taking aspects from various textbooks and also contemporary research that is happening currently. So as always, class notes is the most important reference. So the three important books that I will be following is this is called Physical Properties of Crystals by J.F. Nye. This is a very classic book that introduces people to how properties of various materials come about from a very crystallographic and a thermodynamic point of view. Then so we also look at this book. So we try to understand the symmetry in various crystals and materials. So we follow this book. This is an easy to read book. This is called Space Groups for Solid State Scientists by Burns and Glaser. This is an easy to read book, so that's the reason why for such an interdisciplinary audience, so to understand a bit of material structure and crystallography and symmetry, this is a very well recommended book. And then towards the end of the course, I will be going into looking at properties, how the properties of various materials come about and so on and so forth. For that, I will be following this book. This is called Electronic Properties of Engineering Materials by James Livingston. And there is another book that I don't have it with me now, that's called The Kinetics of Materials by Ballufi. That's quite hard to read, but so the way I will do it in this course is it will make it easier for you to go back, read that book and try to understand what they are saying. So the rest of them are going to be sort of reference. We reference to some of the topics in solid state physics by Charles Kittel, Ashcroft and Mermin, and phase transitions by Yeomans and so on and so forth. So we refer to them and come back, so that's why I didn't bold them here if you look at it. And so the resources that we'll be using, if you're taking this course, I would like you to download this right away. So this is a software called Vesta. Vesta is useful for you to visualize crystal structures and try to understand where different atoms are placed, how do you visualize it in 3 dimensions and so on and so forth. It's a very useful tool to understand the aspects of symmetry and crystal structure that we'll be dealing with in the first part of this course. Okay. So with that, let me tell you what this course is all about. So, this is sort of a very populated slide, but so to be very brief about this course will be organized into 4 parts. So, module 1, module 2, module 3 and module 4, right. So, first we start with what is meant by property of a material. So, we try to formally define what properties of materials are, and in module 1 we try to look at various different properties of materials. These can be optical properties such as refractive index, this can be electronic properties such as the dielectric constant or capacitance of a material or susceptibility, or this can be a mechanical property such as stiffness or compliance of a material and so on and so forth. It does not matter what the property is, right. So what we will see is there is a framework, there is a fundamental framework that comes from symmetry and structure of the materials that allows us to predict what sort of properties can a material have and what sort of properties can a material not have, right. So, for that we first need to understand what is a property, and then so how is it related to the material structure and symmetry. So, we will spend quite a bit of time trying to understand that to start with. Then, so the symmetry aspects actually tell us whether a property exists or does not exist, right. So, whether my material is piezoelectric, forget, so if you do not understand what piezoelectricity is right now, no need to worry, we are going to go into details of this in this course. So, is my material piezoelectric or not piezoelectric, right. So aspects of symmetry tells me these sort of things. Does my material have a component of conductivity in a certain direction or does it not, right. So these are the issues that it will say, but it will not exactly tell me how piezoelectric is my material, right. So, if I give you 2 materials, both of which are piezoelectric, symmetry just tells me that both of them are piezoelectric, right, but is this more piezoelectric than this, right. So those sort of things, those sort of insights you do not just directly get from structure and symmetry. For that we need to look at a bit of thermodynamics, right. So that takes us to module 2, which is so we try to predict what is the magnitude of these properties, equilibrium properties that derive out of thermodynamics, materials thermodynamics, and we try to look at the framework, the unifying framework to actually predict how large or how small the properties are in my material, right. And from here we also actually do a bit of statistical mechanics, right. So statistical mechanics is like the father of thermodynamics, although thermodynamics came first, statistical mechanics came next, but so the empirical, the so-called empirical aspects of thermodynamics is explained in detail in statistical mechanics. So we take recourse to a bit of stat mech and try to understand what is the origin of these properties, some of these properties what are called equilibrium properties, non-dissipative properties, and so how can I say that my material will have a larger amount of this property or a smaller amount of this property, right. So that's going to be the part of module 2. In module 3 I go and talk about what are called dissipative properties. Module 2 is all about thermodynamic or conservative properties. So these properties are those properties, so again I have to define what a property is, but there is no loss of energy when I am talking about these properties, whereas dissipative properties such as conductivity, thermal conductivity, diffusivity, etc. In various materials, so here I am talking about energy losses, right. So these have 2 different frameworks of trying to so the thermodynamics tells us all about equilibrium properties, the kinetics or the Onsager's formulation tells us more about the dissipative properties. So we will actually look at properties that are dissipative in nature, right. Then we will try to look at the relation between so for example, just to give you an example, a conservative property, capacitance of a material. So if you remember your basic electronics engineering or basic physics, you were taught that the capacitance or a material is a capacitor if it can store energy, it is not losing its energy, right. So it stores, the material is able to store the electrical energy that you are inputting in the form of a voltage from a battery as some sort of a polarization, or it's able to store it, right. Whereas a resistor on the other hand, you apply the same electrical energy, it will dissipate the energy, right. So it will flow electrical current and dissipate the energy in the form of heat, right. Now, both of them are related to electronic, these are all electrical properties. So, how is my electrical energy being so capacitive materials or capacitors actually store the electrical energy, resistors actually dissipate the electrical energy. So, they seem to have some sort of so both of them are doing something to electrical energy, right. So, it turns out that one is a dissipative property, the resistance or conductivity of a material is a dissipative property, and capacitance is a conservative property, and it turns out that both are related in some sense, and that is going to be the fourth module. So, it is not that the dissipation and conservative properties are somehow unrelated. There is this beautiful framework called Kramer's Kronig framework, which tries to relate properties, the conservative and the dissipative properties, which are dissipating the same form of energy, either mechanical or electrical or electromechanical, and so on and so forth. Okay. So, we will try to look at that, and then we will try to look at how to actually measure these properties. So if I measure capacitance of a material at almost at DC frequencies, it is not going to be exactly the same as if I measure the capacitance of material at some megahertz frequencies, right. So, the material property actually depends on so what is the input that I am giving. So, what is the frequency of the cause function or the input function that I am giving, right. So, all these properties tend to be frequency dependent, and because of frequency dependence we can use techniques of spectroscopy to actually understand the dispersion in these properties, and that will be module 4. Okay. So, this is a brief overview of what this course is going to be. If you did not understand a part of what I just said, that is okay, because we are going to again do everything in detail. Okay. Okay. So, with that, let us actually now begin. With that small introduction, let us begin the course. Let me go back to. So, let us begin this course by asking the question, what is a material's property? Let us try to formally define this. Okay, since it is a question, I write it in red, and to actually know what is a material's property, I need to have what is called a cause, and there should be an effect, right. And the property is what relates the cause to the effect. So, something like property times cause will be the effect, right. So, example, let us start with a spring mass system, right. So, there is a spring, there is a mass attached to it. Okay. So, this is a mechanical system. This is our favorite example throughout this. This is going to be our favorite example throughout the course. It is easy to understand. And the spring mass system, I displace it, right, to a displacement d or x, right. So, x is the strain, right. So, strain is displacement, the change in displacement by original length of the spring, or displacement d. D is actually called displacement. Okay. So, if I take a spring and then displace it, what is the effect? The effect is that on this spring, right, I am generating a restoring force F, which is in this direction. F is the restoring force. As a result, I have a cause which is D, I have an effect which is F, or the restoring force, and I have a property of the spring which is the spring constant K, which relates the cause and the effect, right. So, there is a cause, there is an effect, and both of them are related to each other by what is called the response function. So, if I apply some sort of if I apply some sort of a temperature gradient to the material, right. So, I am putting in some heat into the material. So, how much heat am I putting into the material, or how much enthalpy am I putting into the material by changing the temperature of the material, that is given as Cp times delta T, right. Now, Cp is a material property, it is a response function, it is relating my cause to effect, right. Now, if my cause is again change in temperature, so with change in temperature, so I can expand and contract materials, right. So, by heating, so I have what is called thermal expansion. So, materials expand, and so I can look at the expansion in material as just a strain, right. So by strain, I'll use the okay. So displacement, maybe I have to be careful with my notation. Displacement will be d, k d, strain will be x, and strain is nothing but change in displacement per unit displacement, right. So so I have some strain in the material, and this strain in the material is related to change in temperature. If I am changing the temperature, the material strains or the material expands. If I am heating it, if I am cooling it, the material contracts, and so the alpha is the coefficient of thermal expansion. So the cause is delta T, or the change in temperature, the effect is x, or the strain that I am causing in the material, right. So I mean, that so railway tracks, for example, expand, and in summer they try to bend. That's why so you make these metallic railway tracks only into segments, and then you combine these segments using what are called fish plates, so that you account for this expansion that happens in summer. Okay, so that's the property alpha, or alpha is the coefficient of thermal expansion. That's the property. Cp is heat capacity at constant pressure. That's the property. Then what happens if I apply pressure to the material? So if I compress the material, the volume of the material will change, right. So so the pressure and volume are supposed to be conjugate quantities of each other, which means if I apply pressure to the material, immediately the effect will be change in volume. So pressure is the cause, change in volume is the effect, right. Now different materials expand or compress differently when I apply pressure. So what is the property of the material that tells me so how much pressure I need to apply to compress the material? So for example, if I take a softer material, by applying the same amount of pressure, it will compress even more. If I take a harder material, by applying the same amount of pressure, it will compress less, right. So this is our physical intuition. So if I look at delta V by V, which is the change in volume per unit volume, again a volumetric strain, if that is my effect, the cause is pressure, the quantity that relates change in pressure to change in volume is what is called isothermal compressibility, or beta, right. So minus beta delta P. If beta is large, that is my material is very easily compressible, so I apply even a little amount of pressure, the material will compress a lot, right. So the change in volume or the volumetric strain is a lot. If beta is small, the material is hard to compress, right. So it's a sort of a harder material. So beta is a property of the material, right. Okay, so these are all mechanical thermal effects. Now okay, so there is something. So now let us look at what happens to a material when I apply an electric field, right. So this is my standard capacitor. What happens to a capacitor when I apply an electric field? Let me just write it completely. Okay, so electric field, or in some sense voltage. So we know the constitutive equation of a capacitor, Q equal to CV. If I apply voltage to a capacitor, I am generating charge on the plates of a capacitor. So a capacitor can be imagined to be two parallel plates with some material in between. It's a dielectric material in between, and then I apply some sort of a voltage, right. So I apply with a battery in between these two plates. These are just metallic plates. Okay, So, by applying voltage, what I am doing is I am actually putting some positive charges on this plate and negative charges on this plate. So, I am actually storing charge, right. So, how much charge am I storing? That is Q. Let me write it properly. Sorry. Now, that Q is given as C times V, where C is the capacitance of the material, right. Now, we can also sort of make this same equation geometry independent and write it as what is called D, or the displacement charges. We will actually look in detail as what these displacement charges are, is nothing but the dielectric constant of the material times the electric field, right. So, the material property here is the dielectric constant, which is relating, dielectric constant and this dielectric constant is relating my applied electric field, that is the cause, and the effect is the charge that I am generating, or displacement charges in some sense are nothing but the charges that you put on these plates, on these parallel plates, divided by the area of this parallel plate. So, it is some geometry normalized quantity. Okay. So, charge density, right, charge density on the parallel plates. Okay. We will come back to this, right. So, we will actually look at the mechanism of how this charge is being generated, etc., very soon, but for now, so if E is the cause, D is the effect, epsilon is the response function that relates the cause to the effect, right. So, we are just, the other thing that I have been tacitly doing but not been telling you is that I am just assuming that the cause and effect, this is the assumption, cause and effect are related linearly. I am looking at what is called linear response. Okay. I am just going to relax this assumption very soon. It does not need to be linear, right. So, I can have a nonlinear response and I will have properties that are also nonlinear in nature, right. So, but I mean, so just to introduce to you, so I start with these linear functions, but by class 2 or class 3 I will be going into some nonlinear response functions that also have interesting so that are also interesting property wise. Okay. So, that is from an electrical point of view, right. So, these are thermal properties, these are sort of so thermodynamic properties in some sense. I apply pressure, I change volume, so there is some mechanics here going on. These are electrical properties. Okay. Let us come back to again our favorite mechanical properties. So, I apply strain, I get stress, right. So, this is stress, this is strain. If I relate them linearly in what are called linear elastic materials, what relates stress and strain? The modulus, right. So, modulus times strain is stress, or Young's. So, if I am doing a tensile testing experiment, so under tensile strain, tensile testing, so I have a tensile stress which is related to strain through a modulus, and this modulus is called Young's modulus. In general, this is called stiffness, right. So, I'll call it C for the time being. So, C is nothing but the stiffness. In general, meaning I do not need to do a tensile testing experiment, I can do any sort of, I can apply any sort of strain and get any form of stress. And very soon I will impress upon the fact that the stress and strain are actually tensors, right. So, it can be shear stress, it can be biaxial state of stress, whatever be the state of stress, or whatever be the state of strain. If I apply strain, I am generating stress, and these two are related through the stiffness of the material, right. So, stiffness is the property of a material. Okay. So, now there are these other kinds of properties. So okay, so in all these properties, right, so these are all, so whatever I have described so far are sort of, so I apply something and then the material responds. So I stretch the spring by an amount x, and so the material should apply a force counterbalancing this stretching that I have done, right. So that there is some sort of an equilibrium that is developing. So here also, so I strain the material, and the material responds by generating equivalent amount of stress so as to maintain equilibrium, right. So nothing is, so these are all sort of equilibrium properties. I apply an electric field on a capacitor, the capacitor generates enough charges so that the entire system is in some sort of an equilibrium. Okay. So all these things that I have shown so far are equilibrium properties. Again, we will formally define what these equilibrium properties are. The purpose of this is to just show that there is a cause, there is an effect, and the quantity that relates, or the response that relates cause and effect, is a property, right. So that's the formally I am defining that as the property, right. So band gap is, in this course I am not going to say that band gap of a material is a property of the material, right. So property is the resistance of the material, or so the capacitance of the material, and so on and so forth. Now that gives me a good segue to actually talk about these properties which are more sort of dissipative, and the poster child for this is resistance of the material, right. So if I apply what is Ohm's law, I apply voltage, I generate current, right. So so the voltage and current are related by conductivity, or so V equal to IR in some sense, right. Or in this case, actually what I am doing is I am doing the opposite experiment, where I am applying current. Okay, so I say like this, I am applying current and I am generating voltage in my circuit, right. So and then so if I just have a resistor in my circuit, if I am passing current through this circuit, I will create some sort of a potential difference between these two terminals. So this is V, this is 0. So the voltage that I am generating is going to be V equal to Ri, right. So where R is again a property. Right. Now in other words, right, so if I am so if I have to make this geometry independent, just like I made my capacitance geometry independent, if I am applying electric field, if I am applying some sort of a current density J, that is current per unit area, J equal to I by A, right, and I am measuring the corresponding electric field is nothing but V by D, or so the voltage drop across a certain thickness of the material, right. So that will be equal to so rho times, rho is nothing but the resistivity. Okay. So here actually pay attention to this fact, here J is my cause, or the current density that I am applying is the cause, and rho is the effect, E is the effect. Okay. I can sort of switch this around, right. So instead of doing an experiment where I pass current and measure voltage across these two terminals, I am measuring voltage and I am passing current. If I do a reverse experiment where I am actually applying voltage and measuring current, right. So across this segment. So what is I? I is being measured and voltage is being applied. Then I have the standard Ohm's law written as J equal to sigma E. Here E is my cause, J is my effect, and what I have is actually the conductivity of the material, right. So it is not resistivity, it is conductivity. So so if I am measuring, so very technically speaking, now I am going to argue that resistivity and conductivity are inverse of each other in a linear case, right. But very strictly speaking, if I have to measure the conductivity of the material, the experiment I should do is to apply voltage and measure current. If I have to measure the resistivity of the material, the experiment I should do is to apply current and measure voltage, right. So the cause and effect change in that sense, right, and this becomes really important if I am talking about nonlinear, so if the conductivity is a bit nonlinear, or so the device characteristics are a bit nonlinear and so on and so forth. These are not one and the same. It's just not a simple inverse. Sigma is not just rho inverse, right. Okay. So so what is happening here in general? What is happening here is, so I have applied, let us say in this case, I have applied a force which is my electric field on carriers, or something that is moving, and this electric field makes carriers move. Carriers meaning electrons or holes, or so ions or whatever they may be. So it is making carriers move. So what I am creating is a flux of carriers. So the current actually measures the flux of carriers, right. So I have a force and I am creating a flux. The cause is a force, but I am not settling into some sort of an equilibrium, right. So now contrast it with so cause is a force here, and the effect is some sort of a flux. Okay. Contrast it with capacitance, where so this is what happens in resistance. Okay. In case of capacitance, cause is a force, or cause is electric field, and effect is some sort of a dipole moment or charge separation. That is it. There is no flow. There is no flow of current. I am just separating the charges. That is it. So I put positive charges on the plate above, and I put negative charges on the plate below. That is it. So I am just doing some sort of charge separation, or I am creating charge. I am not flowing the charges. Here there is a flux of charges. Okay. So this is capacitance, right. So again, so if there is a force and there is a flux of something, these properties tend to be what are called dissipative properties. Okay. So resistance is one of them. So if cause is a force and response is effect is flux, then the response function is dissipative in nature. Do we have dissipative property? Again, we will go into what dissipative properties are, but so here I am just saying that so I am just introducing you to what is going to come. Okay. Now what are the other dissipative properties? See, I can have a gradient of temperature, right. So gradient of T, which is nothing but dou T by dou X in some sense, right. So X cap plus dou T by dou Y cap plus dou T by dou Z cap, which means so across a material I have so this is a T1, this is a T2. So very simply, in a linear case, the gradient is nothing but T2 by T1 by divided by the length or the distance between these two ends, right. So that is the gradient of temperature. I have a gradient of temperature and I am going to create a flux of heat, right. So there is going to be heat flow, and so if there is going to be heat flow, I am going to write it as Q dot. These two are related by again a thermal conductivity. The property, again it is a dissipative property, here is thermal conductivity, right. Again I am coming back to thermal properties, but you see that there is a form, there is a cause, which is gradient of temperature is the cause here, or that is my force, and then the force is actually creating a flux of heat. This is flux of heat or heat flow in some sense, right. So the property that relates these two is thermal conductivity, and so if you have studied a bit of heat transfer, this is what is called Fourier's law of heat conduction, first law of heat conduction. Okay. So we will continue this in the next lecture, but the takeaway point here is, so I have shown you a variety of properties which are mechanical, which have a mechanical cause, mechanical effect, electrical cause, electrical effect, right, a thermodynamic cause, a thermal cause, thermal effect. But a property in general relates any sort of cause to a corresponding effect, right. If I push you and then you fall down, right. So, how you fall down, how easily or how hard you fall down depends on you, right. So, that it depends on your property or your response function, and that response function is what we define today in the rest of this course as a property of the material. Okay. So, with that we will end here and we will take up we will start from here in the next lecture. Thank you.